Well, for those of you who didn't make to it, um, I forgot to hit record button. Sorry, but the reason to actually show up to class on time. Um, just big categories. There's random access memory, read-only memory. Read-only memory includes things like flash, magnetic hard disks, optical drives. Big idea is it takes a different strength of signal to write than to read. So it's more effort to do a write than a read. Sometimes like opticals, you can only do it once. Some of the old programmable ROMs were, um, some of them were just, a read once thing, a straight PROM. Um, but we then added, so like an EEPROM, an electrical programmable read-only memory, has these fuses. If the fuse is resettable, we called it an electronically erasable programmable read-only memory, EEPROM. The EPROMs you could reset, but the only way you could reset them was actually by applying ultraviolet light. So the old EPROMs, when you put a high enough voltage, you blew the fuse. To reset the fuse, you had to expose ultraviolet light to it, which would then cause a transition to occur inside that blown fuse, and it would reconnect again. So we had these old boxes that had ultraviolet lights in the top. And there was usually a piece of tape over the top and a clear window. So if you ever see those chips that have a clear window on the top, those are electrical programmable read-only memories. And when you're done programming it, you put the tape over it so light won't erase your program. And when you want to erase it, you remove the opaque tape over it, and you would stick it in these ultraviolet light tubes, turn them on, and you'd set a timer. They usually had the timer on the outside, and when it dinged, it had run long enough to do all the erasing. So uh, I see Justin says, sorry for not responding. He's eating. No problems. Eating's a good way to stay awake. I just want to make sure everybody's hearing it and understanding the ideas. So, Flash, kind of the modern, what you have with the thumb drive, um, is the latest generation idea of these PROMs, where you can write with one voltage and read with another. So it's a specialized type of EEPROM, if you think of it, but it doesn't use straight fuse technology. There's even newer ones that are coming out that people are working on for what's called memristors. Memristors um, have they store resistance as a function of memory. So they're kind of a cool thing. There's actually four fundamental uh, passive circuit elements: resistor, capacitor, inductor, and memristor. Memristors were theoretical from the mid 70s. They were predicted, but nobody could build them. Um, about 2006 or so, the first memristor was actually built. And it turns out the smaller you get, the better they work. So that's why they're kind of thought of as the next generation of these. You have a programming wire and you have a bunch of other wires that just kind of go over the top. And it literally, if you look at them, they look like this. So there's an under wire and there's an over. You put enough resistance to this lower wire, the field will change the uh, the alignment inside these individual wires here. So depending on what your how you set this field, you can make these wires have different resistances by either aligning or not aligning the cells inside the individual grain wires. So you can then just read out what was programmed on this program wire um, by running a small voltage through. And if the resistance is higher, you'll get less coming out. And if it's lower, more will come through. Um, this is stupidly fast. It works better as you get smaller. Um, Long-term storage, it's a passive storage element. It's got a lot of awesome things to it. Danger is it's difficult to build. So right now um, we're moving that way because it's got a lot of features, but people are having to kind of make it more systematized. So that's kind of read-only memory in a nutshell. Um, this is not our biggest interest here, but as I've mentioned before, it's really the only time I can cover this, and it's just good to be knowledgeable on the general technology that's out there. Most of our interest is going to be up here in RAM. As I mentioned when I wrote this up, RAM has kind of two groups. The first one is the one we've been dealing with so far, static RAM. So we have like our SR flip-flop. Well, this is an SR latch, eventually putting the on in that. We can turn this into an SR flip-flop. But it's the S is for static, and that static is important because this is a powered circuit. Um, it actually makes it for a very stable one. It's also, since it has power driving it, it makes it very, very fast. So driven circuits tend to be quicker circuits. So SRAMs are stable and they're fast and all kinds of great stuff like that. So the question is, with so many great things, why would I want anything else? So let me ask you, if I told you that situation, hey, we've got this stuff, we understand it, we know how to build it, it's really fast, it's really stable, awesome stuff. Why might you ever want anything else? Anybody got any ideas? From Alexander, energy costs too great. Yes, that is one of the things. You're exactly right. So that is one of our big ones. Energy slash power, right, tends to be very high for SRAM. The second we say energy is big, what else does that imply? Temperature, heat. Yeah, I see several people saying stuff. You're exactly right. Whenever energy is here, heat is a problem, right? So people will say energy or power and heat, and totally, totally correct. Um, you know, those are two of those big issues, and those are huge issues. So this takes a lot of energy, which means you need stronger power lines coming into this. Everything else means it generates more heat. That's all kinds of problems there. There's one other thing that's not directly related to these. Maybe you'll guess it, maybe you won't. There's another big issue to us that we have. It's kind of a general one. So energy or power and heat is one big category. Anybody think of another big category that we generally care about? Size. That's awesome. So thank you, Ashley. Great job. Yeah, the size of the thing is the other really big disadvantage. Each of these gates, the smallest I can really build a practical version of one of these NOR gates is with 3 transistors, which means the size of an SRAM is at least 6 transistors. Dead minimum. I can't make it really practically smaller than that. Um, and that may sound pretty small, and it is small, but if I want to make tons and tons of these, I want to get, in order to let you have gigabytes of memory or more, I need to be able to get smaller than 6 transistors. And you might ask, well, what's better than 6 transistors? How about 1 transistor? Right. So if I've got 1 transistor, size goes down. Right. Um, Energy and heat. Well, I've obviously got less transistors. I'm going to have less there, but I'm going to make it even cheaper than that, heat wise, so that I don't have any active elements. I'll only give this power when I want it to have power. Right. So that means that if I'm going to do something like that, this is only going to get power when I want it. I have to be storing the output, not in a driven electrical circuit because I'm not driving it. So I need to be able to get some fundamental device. And we've had this other type of memory. This is what makes up the main RAM in your computer is this new type we're about to talk about here. Um, but I need something that holds things. We didn't have memristors at the time, so I couldn't use memristors as it. And we're really kind of still developing that technology. Can you think of another fundamental passive device, because I'm not driven, that's able to store stuff? No guesses? Come on, what's our fundamental components? Let's see if I can make my chat window bigger. Okay, got a much bigger chat window so I can get all those great insightful answers from people. But still waiting for those great insightful answers. So think about it. Let's break them down, right? What type of passive elements do we have? I mentioned one, the newest one, most of you probably had not heard of before this, called memristors. Maybe you had, but it's much less used, and we don't just have components to use them. Has everybody had a circuits course yet of any type? Okay, so people have had some circuit ones, right? When you first start off, what do we mention? For instance, one of the first things we usually talk about is Ohm's law. What's the component that's resistors? Okay, so resistor is a passive element, right? It does not require you to supply power to it to work. A resistor just is. It does what it does, right? So our fundamental components, we have resistors. What else do we have? Like we said, transistors require you to supply it power. So this is not a passive one. Inductors. And what's our final one? Yep. Caps, capacitors. All right. So which of these store something? Okay, capacitors definitely do. Does anybody else, does any of these other ones store things? Well, a little. Yeah, you're right. Which one stores something a little? Does a resistor store anything? The inductor. Yeah. So inductors also store things, right? Capacitors store things by you put charges on the plates and it's therefore stored, right, by the charges that you've placed on the plates. Um, you probably type a lot better than I do, but I know that feeling. I typo all the time. Don't worry about it. I'm dyslexic too. I'll misspell anything if I get the chance. Um, so capacitors store stuff by charge on plates. How do inductors store things? They store it in the field, right? Yeah, right. So it's all stored in that electromagnetic field, right? You make the coil. As you run the current through it, it'll develop a field. If I turn the current off, I stop supplying energy to it. The inductor will take that field and it'll start breaking it down to get current flow again. And so, um, as long as that field lasts, away we go. Um, so we're only going to want the capacitor as soon as you disconnect it, the charges will start dissociating through whatever you have as your buffer material between them, what's called leakage currents, till the plates are drained off. So both of them are going to discharge over time. We only want to use one of them though. Anybody know which one we like and why? No guesses? We're going to like capacitors. All right. Yeah, you've seen a lot more capacitors in circuits. You're exactly correct. So that tells you what we prefer. Now the question is, why do we prefer that? What happens when I put two inductors next to each other? Yeah, right. So that interference, in particular, we have what's called mutual inductance. So as I build the field in one, right, I run current through it, and it develops a field around it, right? I'm gonna erase the static RAM. We've been doing that a whole ton, so hopefully everybody feels comfortable. So you can imagine if I've got an inductor, right, coiled wire, I run a current through this one, it's going to build up this magnetic field, right, electromagnetic field. Technically, if I've got another inductor nearby, even if there's no current flowing through this, as this one's field builds up, it's going to cross into the next one. And as this field crosses these wires, it's going to induce a current. So it'll actually start kind of bleeding the values across them. It's very difficult to isolate these. To isolate them, you have to build like a Faraday cage around them, right? Put a metal shielding and ground it and all kinds of stuff like that. So it's very hard to keep inductors isolated. We don't like that. We don't want, because I wrote a one next to a zero, I don't want to weaken my one and make my zero become more like a one, right? I don't like that. Capacitors are much easier to isolate. I can make them smaller. I don't need as much protection around. So because of that, capacitors are what I'm going to do. Right? So I'm going to use one transistor and one capacitor to build this. Now behold the magic, right? So if we're okay, I'm gonna erase this and I'll show you how to build um, this. And if you keep in mind this idea that this capacitor is not gonna be perfect, we'll see where the name is gonna come from. All right. So you can imagine I can take a capacitor and just by having a single wire, hook it to ground, I can put a charge on this plate. And if I charge this plate, I can call it a one. And if I discharge the plate so there's no charge, I can call it a zero. Right? So I can give it that kind of name of, there is a charge, there's not a charge. That becomes my 0, 1. Now, if I put a bunch of electrons on here, we'll talk about how in a sec, but I could by just connecting this, right? This will hold. Eventually, it'll start leaking through and it'll discharge. So that means if I were to plot the voltage over time, right, I program it because the voltage is, remember, CV equals Q. Q is the charge. So the more charges I put, the higher the voltage. So as the voltage versus time graph, as it drops, it's telling you how the charges are dropping. And it drops off as an exponential, right? So if you think that, a one is defined as kind of this whole range and a zero is down here, and this is that kind of in between buffer zone between my zero and one, where if it gets in here, I go, uh-oh, I don't know what it is anymore. Uh, well, up here, this is the last time it's good. So my value is dropping. So I at some point have to add more charge back in, recharge this circuit, and it'll start draining again. And I'll have to recharge it and it'll start draining again. And I have to recharge it and it'll start draining again. Right? So this is constantly draining and I have to recharge it. And as long as this time period is long enough that I'm not basically continuously doing this, this could be, thousands of cycles at my nanosecond range. So this can still become a reasonable time period to my device. But that makes this possible. But since it's always changing, we call it dynamic as opposed to static. So dynamic RAM, which becomes DRAM, just taking the first letter, right? So we've got SRAM, static RAM. That means those latches or flip-flops so far. Dynamic RAM. Dynamic RAM basically uses this capacitor. And maybe I'll put this over here so I have a little bit of room. Now I have to have a way of connecting or disconnecting this, um, because otherwise, if I've got something here, the charge can also come back out. So I'm going to have a line that this is going to be my read write line. I erase my voltage decay here. So this is my read write line. And then I need a way of hooking this to the read write line, but I don't want always hooked up. So I'm going to use that single transistor. Right? Then I can apply a voltage here. When I want to be able to read it, it'll open this gate up and the charge can flow out. That means I need a second line, which is right, a strobe, or we sometimes call it an address line. Right. It can be called an enable, but basically if I apply voltage here, it'll open this transistor up, which makes it a wire. This charge will flow out onto the line and I can read it. Alternately, if I want to write something, I again activate this line, it opens it up. I can place a voltage on this line and it will pump charge onto here. And then I turn this off and I disconnect the writing value, and I have now written a charge on there. So periodically, at that time period for how long it takes to drain them, I have to read it. So what's left of the charge comes out, I amplify it, and then I write it back in again. So at regular intervals, we have to do this. Um, and that is what makes our dynamic RAM dynamic. This drain, read, rewrite, right? Drain, read, rewrite. We just have to do this constantly. And that's what you're doing when you buy RAM for your computers. You are buying tons of these. It's really, really tiny. Now, the thing that's kind of really cool about this is I can hook a bunch of them on this line. And since they're really ridiculously tiny, I can just have address line after address line coming in here. Right? Um, and then I could just put tons of lines if I want. Every line gives me a bit. Every row gives me more storage locations. I can do just, easily tens of thousands of these. Okay? That makes sense. Okay, I got a yes. All right. So this is the basic setup. So this particular area is your memory cell. Right? And then this is just the connection. Now, a particular note, I said I can just read those charges when they come out. Um, Notice with all these, they're all in the same line too. I can only turn one of these lines on at a time. If I turn one of them on, it's connected. The other ones are disconnected. So I can ignore it. But when I do a read, this is going to be really, really weak. So I have to have a very sensitive device to read it. What we actually do for this is we have an amplification circuit built onto this. And we basically, if you've got your voltage from 0 to 1, we'll move it so it's actually metastable, right in the middle area. So we kind of pump it to half the voltage. And then what will happen when you connect this, if there's, voltage on it or not, if there's voltage on it, i.e. there's charge on it, you'll see it'll kick up a little bit. If there wasn't, it'll kick down as it has to charge it. So that difference of if there was a 1, there was charge on here, up it goes. If there was no charge, it'll put a small charge on and it'll dip down. We take that up or down tendency and then we amplify it. And we just use what's called a differential amplifier. So it's a very weak signal that requires amplification. But I only need one amplifier per line. So that is why we want a whole bunch on here. But that is basically in a nutshell how your basic dynamic RAM works when you buy a whole bunch. Each of those chips has literally millions of these on here, right? And they just, you know, add a bunch of chips together. Okay, good. Okay. So let's take this. I'm just going to call this a cell from now on. I'm going to add one more thing to this. Um, well, let me just actually kind of do one thing on this, and I'll show you the first. This setup right here, to drive this, since I only have one of them on here for my DRAM, I only want one of these active at a time. That's ideal for a decoder. So I can have an address that comes in, however many n bits I want, and that will then go decoder style to line 0, 1, all the way down to 2 to the n minus 1. And then I have over here an enable. I can then use this type of a decoder to then say, great, I put an address in, enable this thing, only one line is going to get active, whatever address you send to it. It'll activate that line, it'll hook that cell up, and away we go. So it's really easy to build this. This is called a one-dimensional memory because I have a single address that accesses them. And this design of a one-dimensional memory, we're going to use a lot of when we go through building different things. So this is kind of a fundamental one. Um, However, it's not particularly the greatest because remember, each of these in here, basically we've got, for this 0, I've got an AND gate. It's just one AND gate, but um, for 0, I have to take all of these N bits and I have to basically invert all of them and hook them in one at a time. So the least significant, the second, all the way on, right? I invert them all, feed them into an AND gate. So if they're all zeros, I get a 1. But that means this AND gate has to have N inputs, right? So don't worry about the picture. It just needs to be small. All you got to remember is that AND gate needs one input for every bit. So I can't get too big of a gate. Otherwise, I have to go to multi-gates and add levels on. That means that limits me to somewhere between 8 to 16 as a reasonable maximum size for most AND gates for driving them. So fairly typical ones are like 10 or 12 bits. That lets us get, well, if it's 10 bits, it's 1K. At 12 bits, it's almost at 5K. It's technically 4096, but you're part way up. Anyway, it's easy to build, say, 1 to 4K. Um, it gets more challenging above that. Well, 1K is stupidly small right now. So that would make not the best implementation for us. So then people went, well, how can I build something a little more efficient? So I'm not going to draw, like I said, I'll just draw boxes when I want this cell here. Um, so what I would really like is, what if I had 1K times 1K? 1K times 1K, right? 1,000 times 1,000 gives me 1,000,000. Now I'm getting to some reasonable values. So what I would like is to have actually 2 of these decoders. So that was called a one-dimensional array. We have what's called a two-dimensional array. So we need a little bit of room here. You'll need a little bit of room over here. Imagine I got my decoder. I'm now going to have a second decoder across the top. So this is my rows. Right, 0, 1, 2. There's n bits here. So it goes down to 2 to the n minus 1. And this one also has n bits. So 0, 1, 2, all the way down to 2 to the n minus 1. Does that basic setup make sense? I haven't drawn any of the magnetic things yet, but this allows me at the cross section, if this is 10, right? If n is equal to 10, then I've got 1,000 rows and 1,000 columns, which means I have 1,000,000 intersections. Right? So 1K by 1K gives me 1 meg. Does that make sense? Yes. Okay. Now what we want to do is we'll have a memory cell in here, and we're going to want to activate off both of these. So both of these have to be enabled in order to enable my cell. Then we're going to have actually an extra output line. I kind of drew these a little close together. Let me slightly space them out here. One. Actually, let me put the one over here. I have room. You imagine I just zoomed in. I have another line that comes out. This is my output. So I've got two selectors, and this is kind of technically the in out. This is my data. I'll just call this data. So I need to draw this one because now I got 3 wires coming in. What makes the difference? I'll draw that down over here. So I've got an input on the top, I've got an input on the left, and I've got an in out on the right. So these two come in, and they both have to be true, so I connect them with an AND gate. So that AND gate, what comes out here means if both of these are true, I'm really accessing this cell. So then I'm going to use that to hook it up. And I'll put my capacitor on this side. So an outline like that. So this is my data line, and this is my row select, and this is my column select. So the only difference from what we had before, other than I've mirrored it, is we just have 2 inputs and we AND them together. So I have to have both of these selected in order for this cell to go. So out of this entire array of, if this is 10 and 10, 1,000,000 elements, a little bit over 1,000,000 actually, only one of them will be active at a time. But I'm only required to have a decoder with 10 inputs to the AND gate, which is within fabricationable design. So that means since I have both of these, I have to have something driving them. Remember, input wires are always a problem to us. So we put an SRAM bank here. So I'm just going to say registers, because registers are always, 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 always SRAM. I have a register here. This is the column address, right? Sometimes called the column strobe, and this is the row address. Now, since they're both size n, I can hook them up, which means I only need a single line coming in of size n. That means less wires coming in. I only have to send half the address. I send the row first and then the columns. So this is where that strobe I was referencing comes in. This is kind of the load command for the row, and that's called a row address. That's the name of the register, row address. And the strobe is the one we use to tell it to load. So row address strobe, it's a wire that comes in. It's usually just labeled RAS. Yeah, not RAC, RAS. There we go. Row address strobe. Similar for the load for my column register is called the column address strobe, CAS. So now I can just send 10 bits and I can have these 2 bits individual bits that say, do I load it? So I send the low order bits here, low order 10, and I set the row address strobe. And then I turn off the row address strobe. I send the 10 bits of the column, and I set the column address strobe. So I just have two transmissions, and I can load both of these. That allows me to send a 20-bit address and access 1 million bits of information. This makes a good basic cell. So then I can just take this same thing and for each of these, I can do an enable, right? And the enable, all I have to do on this is to say, am I going to supply power to this? So each of these has an output enable. And so I can use that enable bit to turn on one of these macro cells to turn the whole group of 1 million at a time on. So on a chip, I can put a whole bunch of these. All of them will get their row and column set simultaneously. And then I can enable the individual bit I want. And I can do that from yet another one. That's called a 2.5D setup, where I have another one of these ones that turns on the whole group by just controlling the output enable of these two. If the output enable is not set, it just floats. And the float is not big enough to open any cells. So it basically turns that whole thing off. So I can then just walk through that one, and I can walk through all the bits. Doing that, another 1K on it, lets me go from 1 million to 1 billion. So I can easily step this type of a structure up by taking copies of these. So this actually becomes practical by doing these kind of groupings. And I can get up to 30 bits if I need to on there. Does it make sense how I can make this 2D type of a memory? So I can see my last several answers have all been from Alexander. Is that a good um I, I get Alexander gets it, and I'm happy to move on. I just want to make sure I'm not dragging a whole bunch of other people along, or that everybody hasn't just fallen asleep on me. Um, is everybody else also getting it? Because this is really one of those cool things. This is what enables you to build large computers. And it's this exact type of a design that's going to be important. When you go to computer organization and design, what you'll have to do is we'll have to hook RAM modules in, and then the CPU is going to say, how do I access it? So it's going to have to do on the memory bus. Um, oh yeah, no problem, Sebastian. I get that you're eating and everything. I just want to, oh, Chick-fil-A too. Good choice. Tasty. Um, I just want to make sure you're all getting it because this idea will carry over. Um, so you'll have the main chip, and it's going to have to send out a request to memory, and that sending out requests that it does, the back and forth communication along that memory bus, is actually what they're sending is this address in two chunks, and then they'll go through and they'll you know, set the appropriate strobes when they go and everything else. Um, and this, sometimes they'll send the whole thing, and then internally it'll take 20 bits and it'll send inside the chip, it'll send 10 at a time. Um, and sometimes they'll take these things and let's say that, this, if this was the high order 10 and this was the low order 10, what I might do is in addition to this, I might actually take the least significant one and run it into, I remember our ALU description. So I'll do an adder with one, and I'll feed it back into itself. So what that does is it just, let's say you want to read a whole bunch of stuff out, right? Um, we set everything up. You read the first address, then you can tell me, go to the next address. And it'll just, you don't have to resend the addresses. It can just automatically say, oh, walk down the entire row. And it can read out, say, for instance, 10 bits for you. It doesn't require any more network traffic. And we call that, since the first setup takes a while and then each additional read is really fast, we call that a burst mode, right? So you'll get into these things and we'll talk about burst RAMs and everything else. And people go, oh my gosh, what's a burst RAM? And if you understand the structure, all we're doing is it's expensive to set it up, but then it's really cheap to just have it automatically read a whole bunch more. So when you get into these and you're dealing with RAMs and caches and all kinds of stuff like that, and we talk about burst transmissions, it's really helpful to have this picture in your mind. So that's why I kind of just want to make sure that this is settled because it's going to become important for later classes. If we're good with this, then I'm going to kind of move on from here because that's really what I need you to know about a RAM setup here, right? This nice 2D, I can do blocks and blocks of these, right? So if I did 8 at a time, I'd have 1 byte hooked together, you know, and I could just read those out along separate lines if I wanted. I could just send you 1 byte at a time, typical for a byte addressable memory, right? And I can just do that by having multiple copies of these and turn them on or off. I can even have their own independent data lines if I really want. All right. If we're good with this, then I will move on. So this is kind of your standard RAM setup. Um, this is really just used for building RAMs in computer. We're not going to use it for any of our special programmable devices. This is just a specialized design that we care about that doesn't easily fit in our other stuff because we get down to different types of passive components. All right, so I don't see any questions. Like star that in your notes though, because you might have to come back in like 6 months to a year, depending on when you do it, to read things. All right. Let's talk about some of the programmable logic devices we have available to us to build things with. I'm going to start from the most basic level. So there's a group of things, um, programmable logic arrays, PALs, and ROMs. ROM here is related to the ROM we did before, but it's going to have a particular structure. It turns out these are all related types of things. And I can think of that ROM as not a memory storage. I can think of it as a way of doing logic. These two names were copyrighted by the first company who did them. So programmable logic arrays and programmable program addressable logic are set names. So there's also, you'll see GLA, general logic array, and general logic, right? You know, you'll see people talk about pals and gals and that. The general one is the generic version that any company can use as a name. The only difference is it technically from the company that invented it, or is it from everybody else who can't use that trademark name? So I'm not going to worry about it. I'm going to call them all PALs and PLAs. And the only difference, again, it's just the order of them. So this was the first one that came out, programmable logic arrays, programmable array logic. So first company designed this, a different company, I don't know which companies they were. This is way, way back, actually, before I was an engineer, right? But sadly, while I was still alive. So I was a little kid, though, if that tells you something. So this one was invented first, and then another company came up with this style. The whole thing, all of them work off of a single basic idea, which is let's take a series of AND gates. And ANDs into OR gates will give us our sum of products form. Then I'm going to have inputs, and we've already used this type of drawing so far. So this is input 1, or maybe I should call it input 0, and I've got input 1. You can have a whole bunch of them. I'm just going to put 2 inputs, and I've got 2 outputs here. Right? Out 0 and out 1. A programmable logic array allows me, remember this single line here, and if I mark it, that means there's really just tons and tons of these wires. I just don't want to draw them. So in this case, there's technically 4 wires, um, but I can actually just mark them. If I have both a programmable array here and a programmable array here, if I have both of them, it's a PLA, right? So this is sometimes called the AND array. And this one is called the OR array. If I have both and OR arrays that I can program, it's a PLA. If I only have the AND array and there are fixed, certain AND gates all go together into a single OR gate, right? It's a fixed thing. This is programmable. This is static, cannot be changed ever, right? As a pattern, then it's a PAL. Right? And a ROM is this is fixed, but this is programmable. So if this is called A and this is called O, PLA has both A and O. PAL has just A, O is fixed, and ROM just has O, A is fixed. That's the difference right there. That's it. That's all of it, right? As far as the building sequence goes. And that's why we say that they're basically kind of on that whole spectrum. So originally we came up with the highest versatility. And then some people noticed, oh, I could just make this kind of static. And, by picking, say, hook 4 of them together, and I could do groups of 4 of them hooked together, right? So that it's kind of fixed. We usually, when we don't have the OR logic and they're hooked, we usually just kind of draw it more like this. Let me just, I said 4 maybe. They're usually kind of drawn this way. And then you have, of course, your inputs. Right. So you still have your AND array, but you're fixed on them. This style here is called a PAL. Right? You only change what goes into the AND gates. And you can have 4 terms. So if you think of your output from your K maps and that, this is well suited to it, right? Basically, I've got, term 1 or term 2 or term 3 or term 4. So you can have up to 4 encirclements inside this. And as long as you got 4, you're good to go. Often this is bigger. It's usually 8. So it's rare when you need more than that. But we do have a way to handle it. I'll show you in a second if it gets bigger than that. But these terms are usually pretty good to cover it. And then I just program each term. Each of these ones will be like, maybe this is X and Y. So maybe I have, X, Y prime, right? So then this is X and this is Y. So I would have X, Y prime, right? So boom, I just made that first term. And you can just go through and program it. They're already ORed together, output. This is a very easy thing to build to do this programming. Like I mentioned, this intersection here, input to output, I don't hook them, I hook them together. Originally, we did fuses. The modern way of doing it is using those transistors we did for RAM. And then I can just put a DRAM cell here, or flash, whichever you want. And then my programmer can actually write, and it writes in either a 0 or 1 to this. And if it writes in a 1, then this is connected. If it writes a 0, it's disconnected. So whatever you store as a memory location goes in. So when you program, you come in on a different area of the chip, and it just stores values to all these different registers. When you're programming your FPGAs, that is exactly what you are doing. when you're hooked to that USB, it is literally taking that bitmap file you generate, bits mapped to the correct location, and it actually hooks these together. So then this is a temporary, it's an X, because it will only last till you turn the power off. Because once you turn the power off, that D flip-flop clears. So that's exactly what your FPGA, this is actually what you see inside FPGAs too for their switching network. Right? Same basic setup. Um, so, this is a really kind of nice, simple way of connecting or disconnecting a wire. And so that's all we do here. And since those wires are always there, if you don't connect it, it's floating. Um, so therefore, it basically has no effect on this AND gate, and it's just ignored. Right? So floating inputs ignored, away it goes. Right? So this is a very easy way to do it. So we use this for this array or this array. Any of these arrays all do this. Does that make sense? Yes. Awesome. Um, so the reason why this is a little more flexible, if you've looked, sometimes when we've done multi-bit ones, like say for instance the state, we might have like 3 or 4. Like if I've got like 7 states, I need 3 state bits to be able to address it. You'll sometimes notice the same term appears in multiple ones of the bits, right? So you can imagine for a PLA which has both of these, just say the in0 and in1 are X and Y for the moment, right? And let's just say I have a 2-bit address. So maybe for my next state logic, so I could use this for next state, right? Next state 0 might be something like have like an X, Y, or some other stuff. And my next state of 1 might also have X, Y, right? Or it even might have XY prime or something of that sort, right? Um, this would be a common term. So I might want to program X, Y, and you know, from this, let's just say take the simple one of this has X, Y, and some other stuff. That would mean both of these would need that same term. So I get to reuse it for both of them. Um, and then they have some second term, and the second term would go here, and the third term here. They could be different on their second term or whatever, right? Um, and if I had extra things like a state bit or something, then I'd include those on other ones when building them up. But a lot of times you will have common terms that are used. And so that allows me for reuse, so I can get a smaller design, which means I need a smaller one of these, which means the latency goes down, the size of my chip goes down, the power goes down, lots of good stuff. So PLAs allow me that kind of more tight design by giving me these. And since these are just hard programmed at the start, they don't take a lot of power. So if that's good, I'm going to mention one other thing, right? So let's say, for instance, I'm looking at this type of a design. I might say, you know, imagine that there was, let's say I had a whole bunch more of these somewhere else. And maybe this one was X, Y, Z, and this one wanted X, Y, Z prime. So, and imagine that I had over here an extra one for Z. Well, I could use 2 different wires that's in here, but like, let's say there's a whole bunch of these going on. I might not want to have to repeat that, or maybe there's some intermediate calculation that involves some other stuff that was in. And so it was even more complicated. But we'll just take this generically here. Imagine I had this kind of little subset. So this wire right here is XY. I could take this and then all you'd have to do is, say for instance, if I want X, Y, Z, you'd go Z, and here is X and Y. So I'd select those two, and this line is now X, Y, Z. Um, Now, on something this simple, it's not a huge advantage, but the feedback over here, while it increases your latency, it increases your flexibility a lot too. So it can allow me to build much more complicated circuits that's in. Um, and one of the nice features is when we do this, we'll usually, to keep it from having a problem, we'll put a D flip-flop here on the output. And the second I put that D flip-flop, it holds it. So I can actually have that be my state bit. So this would be my state line, and this is my next state, and it literally just feeds back into itself directly. So that can allow me to do it. I can even sometimes take this one and interchange it for that. Right? Taking this bit line and feed it in. This is another alternative. Take the output of the whole thing, and they'll sometimes feed that, the output from the, say the first OR might feed back. So you can have a really complicated circuit that's going in. Maybe I do this one and this one. And if I had, you know, X, Y, let's say I had X, Y, Z, or you know, X prime, Y prime, Z, something like that, right? Right, and I've fed it back. That means this fed back signal is now from here, oops, or X prime, Y prime, Z, feeding back. And then I can feed that into another gate if I wanted to get a more complicated circuit. There's a lot of fun things I could do with these feedback lines that gives me even more flexibility. So a lot of ones will have selective ORs or ANDs fed back, allow you to build more complicated circuits from it. Okay. So this is PLA style or GLA. This style here where you just program the ANDs, the ORs fixed, that's PAL, PALs or GALs. The ROMs, like I said, the reason why we can say that this is fixed is this is really, not only is it the AND array, but this is also the address calculation. This, what you're building here, is technically a decoder, right? It's a whole bunch of different address bits you're checking going into an AND gate. So you can think of this section, the AND array, as an address. Well, what if I built this array so it has all possible combinations? Then you don't need an array, you've got all possible combinations. Well, that's a true full-size decoder, and that's what you have on a ROM. So then the only thing that matters is which one of these are connected. Well, instead of making that a calculation that has to go into an OR gate, I can just store these values, 1, 1, 1, 0. So I can have this come in, and this is an address. So I have a fixed input. I'll just do 2-bit style, right? I have X. I get not X here, not X there, X, X. And then I can have Y, right? Not Y, Y. There's a Y, and there's a not Y. So I have 0, 0, right? 0, 1, 1, 0, 1, 1. That's all your possible addresses. That's just a decoder. So I could take this and hard fix it, and then this becomes an activation line. Memory cell where I can store in whatever you want, right? So I can do two output lines here. I wanted 1, 1, so I just go 1, 1. So if this turns on, you wanted those to be 1 because that's what would flow through. If you didn't, it's a 0, it's going into an OR, it's going to be ignored. So who cares? So the next one would be 1, 0. And then let's say this one had an X for whatever reason. Next one down would be, oh, sorry, that is, I guess that one is 1, 0. And I did 2 1 zeros, didn't I? All right. So you just take whatever your values are and you just literally write them into the ROMs for each successive rows. And you just read it 1, 1, 1, 0, 1, 0. You can have as many of these as you want. And this basic idea is what's done ultimately in FPGAs. So this is how they do them. These are also, what are they called, ROMs? They're also sometimes called LUTs, a look up table, because this is, you're basically storing a table. Right? So you can take your logic tables from the very beginning when we wrote those, and we just store them in and just store them directly. We call it a lookup table, and we're basically good to go. So that's what a ROM is. And it is, this ROM turns out to be the easiest one to do because it's, I just prefix this and then you can store what you want. And this is very easy. Again, you can just write these values in, to a flash or to, DMEM that's just stored inside here. And you just don't allow it to change. It's a fixed table that defines your logic element. Okay, we good? Awesome. All right. So that handles all these. These are all by themselves just your most basic form of a programmable device. I'm going to now assume these as kind of my cells, and I'll just call them, for instance, lookup table. So if I take any one of those three as a basic type of a block, I can now take, let me use lookup table because it's the most common, right, which is a ROM. And it's got a certain number of address lines that come in. Very often this number is 4, allows you to store up to 16 different addresses. It's a pretty typical size for these. Usually I have 4 in and say 4 out. Right, so I can store 16 nibbles. Right, so it can do 4 different logic functions of 4 variables each. And so you send in an address value, it stores out what was in that truth table, and out comes the result of your logic function from one memory read. This is an and or type of a thing. So I can take this, for instance, since this is, right, a sum of products, right, it's the output from the ORs. This sum of products, I could decide I want to potentially have a negated sum of products, because remember we have SOP, and there's, what if I want to do encirclements of the zeros? I can negate them to turn zeros to 1, and then do sum of products on the negated Carnot map. To do a negation, I just make an XOR, and I have a D flip-flop here, and you store a 0 if you want sum of products, or a 0. If you want negated sum of products, you store a 1. And a 1 there will just flip whatever comes out. And that's exactly what you want to do with the negated sum of products. Right? What comes out here, we then pass into a D flip-flop. This allows me to do the synchronous thing, because remember, just writing a table, that's like having encirclements of each individual value. It's got errors of type 1 all over the place. So now I synchronize them here, and this is your clock. Now, very often in more complex ones, there's lots of clocks and they mux them, so you can pick which one you want. I'm just going to call it clock and say the clocking blocks can choose what they want. And that means you give it enough time for this to propagate through so it's stable, and then you hit the clock and it reads in the result. Next value. So that basically is how you're removing all the errors. This is what makes FPGA safe. And there's a variety of different ones. They're all part of a group called SPLD. Originally, this meant sequential programmable logic device, just like sequential circuits as opposed to combinational. So PALs and PLAs and ROMs are technically combinational circuits. These ones, since they have a D flip-flop in them, are technically sequential. But this was the basic type, and they're pretty small. So people then took groups of these, and they had a common bus, which just transmits data, and they put a whole bunch of these SPLDs off of them. And they could kind of hook them all together, right? I'm not going to write SPLD in each of these. And then from the bus, it had a bunch of I/O logic, right? Input-output logic to connect off the chip. And this was kind of your basic chip setup. So it had I/O logic, and it had all these SPLDs. And this was much bigger, so they called this a complex programmable logic device because, right, since it had a whole bunch of these little simple SPLDs hooked on a bus with I/O, and they could do all kinds of stuff, it's more complex. People then did what's called a backronym. They came back and they changed SPLD to mean simple programmable logic device. So the original meaning was sequential, to tell you had this D flip. And then when they made bigger versions of it using these buses, they renamed this to the simple. So you'll see some people calling these simple programmable logic devices and sometimes sequential. These are always complex programmable logic devices. And then once they called this simple, they needed a way to mention that there was this D flip-flop. So they sometimes called these registered, right? Because they've got a register on them. So if you hear about a registered programmable logic device, all it means is you've got a PLD with maybe some support circuit and then a register hooked onto it. And then we'll often, to hook them to a bus, we'll just add an output thing, which is a tri-state gate. So it's connected or disconnected, right? And you have what's called an OE, output enable. If you turn this on, it's connected. So this is just our transistor, right? So the triangle is just with the line coming in on the bottom, right? Called a tri-state gate. Is a really fancy way to say I just have a transistor to connect or disconnect them. And I can put a 1 here, and then it'll open this, or I can put a 0 and it closes it. And so usually this output enable is controlled, so you only do it when you want to write to the bus, because then this would hook directly into the bus. So when it's its turn to write on the bus, you set the output enable and it reads what's on the flip-flop. And that allows these to share a smaller interconnection to communicate between each other. That just sends them, they read them. There's often a register on the front end to hold that value till it calculates the next. Does that make sense? Okay, I'll take as good. All right, so this gets kind of cool, right? But this one, I can still only have so many things off a bus. The limiting thing is, if I get too many things off here, I can only send so much communication on this bus before the bus gets all jammed up. So what we'd like is to have, it'd be nice if these two talk all the time, to let them have their own little special bus. This is what an FPGA adds. So the FPGA is going to take the same basic design. It'll be slightly different from one group to the next, but basically you have these logic blocks. They often call them, you know, as a combination one, but I'm just going to call it just say, our kind of fancy lookup table, or a macro cell, they're sometimes called. There's a few different names they use. Well, let's say this has all that lookup table logic, and the D flip-flops and everything. You got this nice little macro cell. that will calculate one thing. Then I'm going to get a whole bunch of them. I'm going to make a giant array of these. So I've got 9 of these macro cells that are kind of hooked together. Then I need to have a way to communicate between them. So I'm going to hook a bunch of wires running all over the place. I'm going to show them a bunch like this. And realize this is more than 3. I'm just drawing 3 for practicality's sake. I have to have a way to kind of determine what goes where. So we have what's called a switching block. I should put MCs here for macro cells. Okay, so this is kind of the basic setup of how most FPGAs, this is the most generic form of logic on an FPGA. And then what you'll do is you'll have the inputs, we'll select certain of these addresses to come in as inputs. And inside here, you can program which ones do you want to read. And then we'll have ones that come out as outputs. And you can determine from output enable, which one do you write to at the moment. That type of a setup is hooked all over the place, right? So we'll have these kind of input and output wedges. I'm just going to kind of draw them this way that are hooked across, and they can determine when they want to read or write. So if I wanted to send, the output of this to the input of this, it's very easy to do. I can cascade them nicely without going here. But if I wanted to send the output of this down to here, I would have to say, for instance, hook this through the switching block so it comes here and it comes in. Does that make sense as a goal? Got confused in the end. Okay, so we've got these macro cells. Let's say this macro cell needs to send its answer to this macro cell. So when you're doing your programming, it's trying to do these, determining the map to send things on. It's possible that this one has to feed into multiple of them. So this one might have to go to this one, and maybe even this one to calculate some net function, right? So this is the first block, and then it's got to go through all 3 of these. So I have to send this value here. It's got to go in here. That's really easy. You just read it. But it's also got to get sent through this switching block to come down and come into this one. And maybe this same signal has to get routed here, and then down to here, and then into that one. So let's say as a result of your calculation, you determine one lookup table isn't big enough. This one has to go to all 3 of these. So I have to make this transmission of the signal to these 3 locations to make it work. Does that goal make sense? We're trying to figure out how to hook them together, because remember, these are, only 4 wires coming in and 4 coming out. So if I need something bigger, they're going to have to cooperate with larger blocks. That makes sense. Okay. So now I've got to be able to say, that's an easy connection, or I just set my output enable and it's on this wire, right? I set my input enable and I can read this block. So I just have another, tri-state gate on here called input enable, and I decide turn that wire on and read it. The question is, how do I route this through this switching block, right? To be able to send it down to here, and then I can input enable. And I also need to send it simultaneously, not just here, but also over here. And this switching block has to send it here. So this is kind of my network. These switching blocks are like routers. So think of these as computers, these as routers, and this, the wires between it, as network cables. So my data basically I get some done on this little tiny computer, and I have to send the answer to a bunch of other computers that are working in parallel with me. on your labs and you see as one of the steps it says routing, that's what it's doing. It's figuring out these lines. It's figuring out how to set these little tiny routers to route the data to the correct location, right? So the first thing it does is figures out what does it need to store. It'll break it up on the macro cells, and then it'll figure out these routing arrays. And then it'll make sure none of these take too long. That's all part of that programming set. So if that makes sense, in order to draw the next stage, I have to erase this. And I'm just going to do this part. Because this we've already talked about. This is really simple. It's just hard fixed, and you have an output and an input selector. Right? That's really easy. So the only complex part is here, because wires just carry things. Right? So I want to draw this switching block big. I don't want to erase this if anybody has any questions. So is it okay to erase this so I can watch this switching block? Yep. All right. Gigantic switching block. Let me just do 3 wires to keep this somewhat simple. So 3 wires on each side. That means all of these are going to need kind of carry through. I've got a gigantic setup of these. And I can't have them all fixed. Now I've got a whole bunch of little wires. And I've got to choose to how am I going to connect these to get from one place to another. Okay? So here are my options. I'm going to draw a little weird little shape here for each one of these. And then I'll show you what I do for, this is going to be a repeated idea. And it'll look kind of like this from a distance. You kind of get these like diamond-like patterns. What I want to do was I had a signal coming from here that had to go here and had to go here. Which means I've got to hook this. Maybe I'll draw this in a different color. I've got to hook this so that this will go, say for instance, from here down to here, over across here, 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 and out, and also down here and here. And I don't want to block this wire or that wire. So I need to have some flexibility that I can allow these to go different routes and I can have multiple things go through. Does that make sense as a goal? Yes. All right. I'm going to draw one of these kind of bigger. I'm going to take this lower portion down here because I'm not using the lower portion. I'm going to draw one of these much, much bigger. Now what I'm going to do is I'm going to take each one of these. I'll hook them up. It is possible that I want this to go to here. So I put a wire between them with my transistor and I hook it to a D flip-flop. So if I put a 1 here, it connects the 2 wires. If I put a 0 here, it disconnects the wires. So I can connect or disconnect. This is the only time I'm going to draw that D flip-flop. The rest of the time, just to keep it from looking ugly, I'm just going to draw the transistor, but each one will have their own D flip-flop. So I might want to connect this wire to this wire. Right? So it'll have one. I might want to connect this to this. I might want to connect this one to this one. I might want to connect straight middle. might want to connect straight across the middle this way. Okay. So to do this, I need 1, 2, 3, 4, 5, 6 D flip-flops and their transistors. Now, if I want to connect, for instance, here, I want to go top to bottom, all I have to do is connect this one here, up here. Right? That still leaves it free for you to connect this side to this side if you wanted. So by going here, I haven't blocked you from using this wire. You can still use it. You're perfectly free. It doesn't cost you anything, right? So I can still route this signal through the middle without interfering. They don't cross over. I just go through the middles. And I just leave the other ones off and they're disconnected and I'm done. Okay? So I can do that one very easily by just using this kind of middle wire right here. So for my signal that we were doing before, right, I'm coming in, I go right through the middle and down. To get through the middle here, I can still go straight down this wire. I want to go out, so I go down the middle again, and then I go out. So I just turn this same one on in these 3 locations. Does that make sense? Also for this middle one, not only do I want this on, but I also want this one on, right? So I have a 1 here, and I have a 1 here. That allows me to simultaneously go through the middle and to go down this side here, which then routes it across. I then use this line on this one. I just store a 1 on that. Goes down this wire. I go down the middle of the next one. I store a 1 on this one and then out. So notice I can now switch by picking whether I store zeros or ones in the appropriate locations. I can do any switching combination I would like to through this. Right? So I have a very generic switching block. Does that make sense? So when it's doing routing, it actually makes these type of switches in here, determines what values to store to the 6D flip-flops needed for every interchange. And we have much bigger interchanges than 3x3, but at 6 locations on each, it's still pretty doable. So now I can program the macro cells for the logic, and I can hook them together and route their signals through these, these nice switching blocks here. The combination of those two, I now have the calculations. I've got D flip-flops in the macro cells, so I have memory, and I've got a switching block, so I can make custom buses whenever I want, because each of these lines a bus and it goes to multiple places. I now have a much more general than a CPLD, right? And since all of these are done with FETs, right, because they're nice and easy, they don't take a lot of power to run. FETs are, field effect transistors. So since we use FETs for everything, we call this a field programmable logic device. FPGA is, field programmable gate array is the technical name. Right? And so that field programmable gates array set up in giant arrays, FPGA. So we started from the most simplest thing, transistors and capacitors, and we're able to, by using those same ideas over and over again of arrays with transistors hooking things up, we're able to build your full FPGAs that you've been programming. You now really have everything you need to know as a concept to technically build your own FPGAs. It's not practical, it's easier to buy it from somebody, but you at least know how the whole thing works. All right, we have now set our time, and I notice I'm a little bit over. Sorry about that. Does everybody feel good about how we build all these different technologies? I'm seeing yeses. So I'm gonna call this good. The recording will hopefully be up sometime tomorrow. It takes a while to process. I hope everybody's doing well. And I'll be watching for questions or other things too. So hope things are great. Everybody stay safe, and I'll see you on Tuesday. God bless all.